All right. So in the last lecture, let me just do a very brief review of the last lecture. In the last lecture, what we did was that we started with a particular example to make the principle clear that there are field theories that appear in the infrared and long distances. And these field theories, once you quantize them, will have particles that have emergent particles, low energy emergent particles that are quasi-particles that could have physical properties such as statistics, mass, dispersion relation that are drastically different compared to the UV system that you were looking at. To make this point clear, we considered a model of solid that was a bunch of atoms that were coupled to each other using nearest neighbor Hamiltonian, and this Hamiltonian we modeled it with as like a, just expanded to a second order. It looked like a interaction like spring attaching two nodes of the two of the atoms, and we wrote down a natural Hamiltonian for it, and we solved it. There was the low energy excitations were phonons. They showed relativistic emergent dispersion, and we discussed this in a little bit more detail. So there was field theory emerging in the infrared with quanta that were very distinct and had very different physical properties compared to the UV theory. So that's what we went over last time. So today, what we're gonna do is we're gonna just get started with quantum field theory as a continuous field theory, and study the equations of motion of this. Sorry, we're gonna consider classical field theory and consider and study the classical equations of motion of it, right? So I'll start with a brief review. We'll spend half an hour reviewing or 20 minutes reviewing relativity and the notation. We'll discuss the action principle in 0 plus 1 dimensional quantum, 0 plus 1 dimensions. So this is the motion of a classical particle in space-time, right? A single particle moving along in space-time, relativistic particle. Then I'll discuss functional calculus, because the same way that you could do calculus, standard calculus for functions and define derivatives and integrals, you can do that with functionals, because you will see that the action is going to become a functional, and then you will have to do functional differentiation. So there's functional calculus, and then we're going to generalize the action principle to d plus 1 dimensions, and then extract the field theory, classical field theory equations of motion, the Euler-Lagrange equations, right? So is the idea of the where we're going with this clear? This is going to be a reformulation of classical mechanics in the language of action principle, and we're going to make a very clear point of why the action principle and field theory is appropriate for field theory, and where does the magic lie? The keyword is locality. So locality is the keyword we're going to emphasize as we go along. All right? Keep this in mind. There are 3 principles I've said that are going to be our guiding principles in constructing quantum field theory. Keep this in mind for the whole course. Locality, relativity, Poincare invariance, right? And then renormalization symmetry. So renormalization, sorry, not symmetry, renormalization, right? These are 3 principles, and we're going to go over them. Today, we're going to put a lot of emphasis on locality, at least classically. All right, so review of relativity. Stop me whenever you feel something is unclear. So here's the notation we're going to use. I'll try to stick to the notation. I might sometimes deviate from this, but hopefully it will become clear from the context. So little d is going to be the dimension of space, and d plus 1 or capital D is going to be the dimension of space-time. We're going to use this relativistic notation where x mu, the mu index, runs over 0 to d, and x0 is the time component of this vector. This is a vector field, and vector x, the spatial component of it, right? And sometimes we write it as xi. Every time we write xi, I runs over the spatial components, right? That's just a canonical convention we're going to use. Now, in space, you're perhaps familiar with rotations. right? So if I pick two spatial directions, say x1 and x2, I can apply a rotation matrix to this. Rotation is described by matrix transformation, which is if I'm rotating by angle theta, this matrix is just simply this thing, cosine theta, minus sine theta, cosine theta, acting on x1, x2, right? So if you have more dimensions, it's going to look like something like this with identity on the rest of the components and zeros elsewhere, right? In matrix notation, you can write this as x prime being R rotation matrix dot x. This is matrix multiplication, right? These are rotations. Now, boosts are very similar to rotations, and I'll try to explain why. Oh, sorry, actually, one more thing. So the rotations in D dimensions form a group. Does anyone know what the group is? It's a group of orthogonal matrices. So in D space dimensions, this is OD, right? Orthogonal D by D matrices. That's the rotation. There is also the thing that's sometimes called SOD. So do think about special orthogonal transformations. Well, how is that different? These are things that we're going to discuss later on when we talk about representation theory of Lorentz group. But for now, just it's a good reminder. I think it should be familiar already. Now, boosts are very similar to rotations, except that here instead of cosine, you have cosh, and instead of sine, you have sinh for some parameter eta, right? So of course, it should be clear that sine of I, some real parameter, you could bring the I, you could bring the I out, and it gives you sinh. And cosine of I parameter is like I cosh, right? So it seems like there's an I floating around, right? But that's just analogy for you guys. So this looks very much like the rotation matrix here, right? Except that it's between it has one leg between time, one leg in time, the other one is some space direction, right? These are boost transformations. This eta parameter, cosh eta parameter, the eta parameter is called rapidity. And if you want to relate it to the standard notation that people use in relativity, cosh of eta is some gamma, and gamma is the inverse square root of 1 minus v squared over c squared, right? So a particle that's moving with velocity v, that is the boost that's here, right? In this course, we're just going to universally set c equal to 1. Sometimes I set h bar equal 1, sometimes I do not. I'll try to be very clear about this. Right? But for all purposes in this course, speed of light is 1. Okay? All right, so again, in matrix notation, this is x prime, which is a vector, is a matrix times another vector, right? So this is how transformation boost acts. More generally, if we put the group of boosts and rotations together, we get a group that's O1, comma D. We'll discuss this later in more detail. This group is called Lorentz transformation. This is basically apply a rotation, an arbitrary rotation, and apply a boost, or apply a bunch of rotations and boosts and combine. Just the most general transformations you could do by mixing boosts and rotations. Okay. And usually we're going to use this notation. Lambda, capital lambda, is going to be as our boost. Our Lorentz transformation, Lorentz matrix. Now, we often in the language of this covariant language I was describing here, right? If you have a vector like this, oh sorry, I think I should put the transpose here. So you have here's your x mu is your initial 4 vector or d plus 1 vector. This is a tensor or matrix in this case that's acting on it to give you the new coordinates, right? And we're using the Einstein convention, which means that repeated indices are summed over. That's going to be universally the case in this course, right? Otherwise there will be a million sums all over the place and it's not convenient. Okay. Now, what is eta mu nu? Eta mu nu lower mu nu. This is flat metric, so it's the time component is 1 and all the spatial components are -1 and the rest are 0. This is flat space metric. I'll try to stick to this convention, but somewhere along the at some point I might switch to the other convention where this is multiplied by -1. Time is -1, the rest is 1. I'll try to stick to this convention, okay? That's something that's really annoying as you go from one textbook to another textbook. Now, we use this metric to bring upper indices to lower indices, right? Again, repeated indices are summed over. So here's some vector with upper indices, and you can write them in terms of vectors with lower indices. Any questions so far? This is just like a review of relativity.
I had a quick clarification for rapidity.
Yes.
Because it's been a while since I've used it. Is positive eta a boost to the right and negative eta a boost to the left?
Positive eta boost to the right. So what is okay?
Like how do you differentiate left and right?
Okay, so yeah, that's the point. So no, it's not like that. So let's see. So the best way to write this down is to do these transformations in the xt coordinates like this, right? And so of course your velocity. So when you do a boost, the only thing that matters is v squared here, right? So your gamma is going to be something positive, right? And then cosh of eta is going to be something negative. Now, it is true that you could use the sine of eta to, actually, sorry. Can you do that? No, I think eta is positive. I think eta is positive. This is, yeah, I have to go back and take a look at this. But you just, when you boost, it's like, yeah, I think eta is positive. But it's a good exercise to write it down and see. These are just the standard transformations. Yep. Okay. Any other questions? All right. Yeah, if this notation is a little bit, you have to remind yourself how it works. Do some Wikipedia level reading or look at your old textbooks.
I have a question.
Yes.
Well, we're using the same symbol for rapidity and the metric, right? And the flat metric, right?
Yeah, but the metric is a tensor, so I'll always write down the parameters. Also, the rapidity I'll never really use in this course. I wrote it in terms of rapidity, so to make the connection to rotations clear, right?
Yes.
But often we write everything in terms of gamma, right? And as a matter of fact, often we just formally deal with these lambda matrices, and you'll actually often we deal with the generators of them, which is boost. So
thank you.
Yeah. All right. So now if you have a d+1 vector, 4 vector, for instance, it has a proper length. Proper length is basically lower and upper v nu contracted. This is like v nu contracted with lower metric, which is basically v naught squared minus the vector part of v squared. So hopefully you guys know what I mean by this. I mean this, right? So vi sum over, right? Repeated indices are summed over. All right. So one important example of such vectors for us is going to be the momentum. Okay, this time I did it right. So it's going to be the momentum 4 vector or d+1 vector. The 0th component of momentum is energy, and the spatial momentum is spatial momentum, right? It's in the other d components, right? P squared. This is perhaps this is a very important equation. So P squared is going to be, by this formula above, is going to be the time component of it, which is E squared, minus the momentum vector squared, right? That has a name, which is m squared. That's the mass of the particle, right? So the mass of the particle, we just identified it as norm of the d plus 1 or 4 vector, right? Norm of a vector is Lorentz invariant. Is that clear to everybody? That's a good, yeah, check that for yourself, right? Normal vectors are Lorentz invariant. All right. Now, in this course, we'll often use inverse metric, and inverse metric is just the inversion is simply defined by lower and upper indices this way. This is Kronecker delta, otherwise known as the identity matrix, right? Now, there is a d plus 1 inner product. This is, I just told you about the norm of a vector, right? Norm of a vector was the proper length. Now, the inner product is just what you get, the inner product that will induce that norm, right? So if I have two vectors, this is the inner product that they have. Now, Lorentz transformations are symmetries of flat space-time. That means that if you apply Lorentz transformation matrices, sandwich the metric, if you transform the metric as a tensor with Lorentz transformation, the metric doesn't change, right? In matrix notation, this is what it looks like, right? So Lorentz transformations preserve the metric. They are the isometries of flat space metric. Good. All right, to continue with relativity, just to set the notation again, as I said, Lorentz group is this generalization of the rotation group where you put O1 comma D. This one is to tell you about how we are combining time versus and space, and these are just the standard OD rotations, and this one has to do with boost, right? Now we usually use this notation for partial derivatives, right? Del mu is del x mu, and then we have a D'Alembertian, which is basically the d plus 1 dimensional version of Laplacian, right? So it's just del t the second derivative time minus the Laplacian and the convention I'm using. We often use it this way, write it this way. Good. So here's an important bit. I will say this, and we'll come back later on when we come back and go over the representation theory of Poincare group, Lorentz group. We're going to discuss it in more detail. We just talked about the action of the Lorentz group and points in space-time, right? So if you have X, lambda is some sort of matrix that acts as that implements the Lorentz transformation and does this following matrix multiplication. Now, how does this act on functions or objects that live on space-time, right? We say a field, so fields that live on space-time. A field is called scalar if under the Lorentz transformation, the new value of it, right, f prime of x prime is basically f of x, right? All you need to do is just transform the point. The value that the function takes in the new point is basically the same, the value. So if I move x to x prime, the value of function at x prime is the same thing that it used to be in point x, right? So the function is scalar, it just itself doesn't change much, just the point, it just tracks the points, right? If it's a vector field, it carries a Lorentz index. So when you multiply, you have to contract these guys. Of course, x goes to x prime, but some overall matrix acts on this vector field, right? This is how vectors transform under a Lorentz transformation. This is not mysterious. If you get yourself confused, think about two-dimensional rotations. It's just how a two vector transforms under a two-dimensional rotation. So take x, y, right? And this is x, y coordinates, and then take a vector and apply a rotation to this cosine theta minus sine theta, cosine theta, right? There's nothing mysterious about this. The vector transforms in a particular way, and that transformation is a vector. That's a vector field, right? More generally, there is more to fields than just scalarian vectors. The the field, we could call it some psi of x, right? It could carry all sorts of indices that I've suppressed here. There could be, I don't know, alpha, beta, all sorts of indices here that take values on discrete values. And then when you apply the Lorentz transformation, x goes to x prime, but overall transformation of the field is represented by some matrix or some tensor acting on the original field with a bunch of index contractions, right? When this happens, we say the field is in a representation of the Lorentz group. When this is a matrix, this S lambda is a matrix, we say it's in a representation of the Lorentz group. If this was quick, we'll come back to this and spend quite a bit of time on this. Right, but this is a generalization of the notion of you could have a scalar, right? You could have a vector, you could have other things, you could have tensors, right? You could have spinors. We'll see that spinors are going to be coming forward. All right, are we good? Any questions? All right, and finally, the last bit I'll just say to review relativity is in classical physics, we have rotation invariance, which says that laws of physics are unchanged under rotation of coordinates. If I'm building a bridge and I'm using F equal ma is the same as the time of the day changes. And meanwhile, the Earth, the Earth is rotating, right? So the Earth is rotating, but F equal ma, the laws of physics are invariant under that, right? I shouldn't care about my orientation in space if I'm writing laws of physics. So this is to be viewed, Lorentz symmetry or Lorentz invariance is to be viewed the same way. That not only rotations leave the laws of physics invariant, but also boost leaves the laws of physics invariant, right? So because this is the general group is O1 comma D, right? Any combination of boosts and symmetries leave the laws of physics invariant, right? So actually the symmetry group is a little bit larger. The symmetry group is the Lorentz group. We just decompose it in rotations and boosts plus translations. Of course, translations are also symmetries that we often talk about, right? Laws of nature also invariant under translations, right? All right. The combination of the Lorentz group and translations is called the Poincaré group, right? I write this plus to just not scare you guys with mathematical notation of cross product, but yeah, just the group you get by having translations and Lorentz transformations is called Poincaré, right? These are symmetries of flat space time quantum field theory. Are we good? Any questions? All right.
Did you clarify these when it's the cross product of the Lorentz group and the translation group, the Poincare group?
Yeah, here there is a cross product, but let's not worry about that. That's just a mathematical construction. It's just the object you get when you combine. Mathematically, it has a name. It's an object you combine all of these guys. Sorry?
You combine these two groups to make one group, so to say.
Correct.
Okay, got it. Thank you.
Sure. That thing is called Poincaré. All right? Okay. So that is my review of relativity. That's brief. I tried to hit all the points that we're going to be using all the time. So just if some of this needs more explanation for you guys, look into it and just make sure that you follow everything up to date. Okay, let's switch gears and talk about principle of least action. So the remainder of this lecture is going to be about principle of least action for the motion of a single particle in space time, and then which is like a 0 plus 1 dimensional field theory, and then generalizing that to higher dimensional field theories that are d plus 1, right? That's the idea. What is this? This is a reformulation of classical mechanics. So for example, in the case of a single particle, all we're doing is that we're reformulating single particle mechanics in a way that is elegant makes locality manifest and makes symmetries manifest. Right? That is the idea. So our particle is a point that moves in space-time, right? So Q is the location of the point, and I can view Q of t as a path that the particle takes in space-time, right? That's what I'm after. The particle starts at point ti, right? Let's say it ends up at point tf, and I want to solve what is the path that it takes in space-time as it goes from between these 2 points, right? That's what I want to solve for. Of course, you could solve this using F equal ma, but there is a more elegant way of doing this, which makes the symmetries more manifest and it's easier to generalize to field theory. This is the action principle. To every path that the particle can take, you associate a number. Let's say a real number. That is called an action, right? So it's a function from path to numbers. This path has a number. This path has a number. This path has a number, right? The path that the particle takes is the smallest number. The path that takes the smallest number is the path that extremizes this function, right? So the one that minimizes this or technically extremizes this, right, is the path that the particle travels. Now, as a function from a path to a number, you could write all sorts of things that we'll call non-local. Now, I want to say, what is a local expression? A function is local if it's an integral of a function at every point along the path. That is a local object, right? If it's a function from a path to a number, I could have a local expression like this. Sorry, right? This is a local expression. Sorry, I wrote this incorrectly. Sorry. This is, I don't know, for example, L of Q of T. This is a local expression, right? Because what I'm doing is that to every moment in time, I associate a value. Then I'm integrating that along the path. I didn't have to do that. I could write down all sorts of expressions like this, right? L of QT1, QT2. I can write down all sorts of things. This is non-local as opposed to this one, which is local. Is the distinction clear? Both of these are functions from a curve, a path, to numbers, right? Both of these are functions, but we're going to stick to locality, right? That is one manifestation of locality. The fact that you could write it as an integral along over time, in this case, over a simpler function, it means that you can write it as that simpler function we call a Lagrangian, right? So this action, a local action, will be an integral from initial time ti to final time tf, dt of a function, which is a function of every point, right? That we're going to call Lagrangian, plus boundary terms, potentially boundary terms. Well, let's forget boundary terms. So boundary terms are just contributions coming from ti and tf. Let's ignore them for now. I will come back and talk about boundary terms, all right? So let's just work with this simple expression. Now, I've put in by hand, already you can see the dependence of this function on the path. I've taken this to depend on qi of t, right? The path, the derivative of qi of the t, which is velocity along the path, right? Velocity that the particle is moving with, and potentially just purely on time, right? This is a local expression, as opposed to all the other double integrals over t, triple integrals, or crazy expressions that could have been. Is the notion of locality here clear? All right. So when I say the minimum, so this function that we're talking about is called action. It's a function from path to numbers, right? The principle of minimum action says that the particle follows a path that minimizes or extremizes the action, which means that so if you want to find an extremum of a function, you have to take its derivative and set it equal to 0. But here you have to take a derivative with respect to variation of the path, right? This is not a standard derivative. This is a functional derivative. So if you had some path qi, for example, this is the path that it takes, you shift every point by some delta qi to get some new path, and you require the first order variation of S under this transformation to be 0, right? That's the principle of least action. So let's go over this in more detail. Here's your delta S. It's an integral. Here's your S, integral over dt of L, right? Now, L was a function of qi, q dot I, and t. Let's for a second assume there is no explicit time dependence. All right, so it's only a function of q of t and q dot of t. If I'm doing a variation, I'll have to take partial derivative of L with respect to qi and partial derivative of L with respect to q dot, because they both depend on t, right? So here's the variational expression I have for delta S, right? Now, this is ddt of q of I. I can complete this and do an integration by part. I can write it as ddt of qi del q dot I, right? Minus this expression I've written down here, right? You just do integration by parts, right? You just you write down this term as this plus a boundary term, right? The first term is unchanged. This guy is unchanged. Now, this is a boundary term. It's a complete derivative. So when you integrate over time, it just ends up being a boundary term. So now recall the original boundary terms I said you can add to your Lagrangian, to your action. Often we add those terms such that they cancel these terms. Often, but we don't have to, right? I just want you guys to remember that in this print, when you do the variation, you have to use integration by parts and you will end up with a boundary term. If you had initially a boundary term, there might be a convenient cancellation or not. Okay? Are we good? Now, the fact that delta S has to be equal to 0, well, we, for a second, let's say we ignore the boundary term, tells you that the bulk term has to be 0, but the bulk term has to be 0 for any delta qi, for any variation. That means that the only way you could arrange for that is that the kernel of it, which is this expression, has to be 0. These are the equations of motion. These are the Euler-Lagrange equations of motion. And I'm going to say in a second that these are the F equal ma that you're familiar with. All right? But are there any questions about this variational principle?
I think on the top of this page, it should be ddt delta qi.
Sorry,
Yeah, on the top right corner.
Top right corner here. Oh, yes.
Yeah.
Thank you. Yes.
Yeah.
Yes, correct. Thank you. Yeah, correct. Thank you. Any other questions?
Yeah, doesn't del qi go to 0 at the boundaries anyway?
In principle, yeah, depends on the boundary. If you put your boundaries far away in time, or if you put the boundaries at far infinity, yes, or you could simply define your QIs. So you could say, I'm allowing, I mean, these are boundary conditions. I'm allowing the path to change, but I'm holding the two endpoints, which means that delta QI at TI and TF are 0, right? So that means that they drop out. But in principle, I make this point of the boundary terms being present because in space, when you do these integrals in higher dimensions, they do matter. They do matter sometimes. You just have to be careful. And I do have a comment about this for those of you guys who are more familiar with dynamical systems and phase space. But yeah. But exactly as you said, if you just think of these variations, that holding Ti and Tf fixed, by definition, delta Qi has to be 0 at Ti and Tf, right? Okay, so here are the Euler-Lagrange equations. I want you guys to stare at this. Another question. All I've done, I'm just dealing with F equal motion of a free particle on and a single particle. This is a single particle classical mechanics. Now, assume that, well, I just assumed already that L does not explicitly depend on T, right? Which means that the partial derivative of L with respect to T is 0. This gives you an example of a Noether theorem. So we're going to go through that step by step. But what is the idea? We're going to spend a whole part of the course on Noether theorem. But the idea is that there are 3 concepts in physics that are related. When you talk about actions, if there exists a transformation that leaves your action invariant, it has an interpretation of a physical interpretation of a symmetry, and it has a physical interpretation of a conserved charge. So you can think of this as a triangle. Conserved charges and symmetries are related, are two sides of the same thing. And then once you talk about mechanics or physics in the language of actions, these are also the same thing as invariance of the action under transformations. This is the content of Noether theorem, but we're going to go over this in more detail, right? Okay, so
by charge, okay, sorry. By charge, do you mean a conserved quantity or
Correct.
something?
Correct. Conserved quantity,
Okay.
in this case, it will be energy. So the point I'm going to try to make is that time translations leave the action invariant. That has an interpretation of as a symmetry, and it means that there is a charge that is preserved, that's conserved. What is that charge? That is energy.
Okay, I see.
Right? Good. So to see this, to make this very manifest, I'm going to change my variables from Q and Q dot of T to QT and P of T. P of T is the momentum conjugate to QI, right? I'm going to play a trick. So this is often called phase space, right? I'm going to play a trick. I want you guys to know that what I'm doing is fully general, okay? At this point, you don't even need to know what P of T means, right? P of T is just some change of variables, right? I know that as a physicist, I have in my mind that the momentum conjugate to QI is defined in the following way, but I'll prove that to you guys. Well, I'll tell you the point of this. I'll try to make the point of why P of I, we define it this way. All right. So I just introduced a new variable P of I, and I'm going to do a Legendre transform of my Lagrangian. If this doesn't tell you much, it means that just given a Lagrangian, define a new function called Hamiltonian, where you basically trade Q dot for P variables. Right? All right. So this is just it's called Legendre transform in math, and you do it outside of the context of physics as well. Why do you do it? For the following reason. Take this function and take a time derivative, right? So you take a time derivative of this term, time derivative of this term. First term will give you 2 terms, the second term will give you 2 terms. You package them in the following form, right? Now you notice the following thing. If I make this choice, if I define my PI this way, this term vanishes. And furthermore, PI dot this term becomes this equation. You recognize this equation. This is the Euler-Lagrange equation we just had. So if I define my PI in this particular way, this term vanishes, the second term vanishes as well because of the Euler-Lagrange equation. Therefore, I end up with the following equation, that Hamiltonian as a function of time is invariant. Mathematically speaking, the invariance of Hamiltonian as a function of time, energy conservation, is equivalent to the following 2 equations. Right? Defining a conjugate variable P dot in the following way, and then satisfying the equations of motion. This is the Hamiltonian formulation of classical mechanics. I could just be totally ignorant about Lagrangians and formulate everything in terms of Hamiltonian and the phase space, right? I say this because in canonical quantization, we are going to use the Hamiltonian quantization, but I wanted to remind you guys that these two things are equivalent. So again, recap. If you define the canonical conjugate this way, then the Euler-Lagrange equations are equivalent to the conservation of Hamiltonian and vice versa. Conservation of energy. Good? Any questions?
One question.
Yes.
But when you go into the Hamiltonian framework, doesn't relativistic invariance become much more muddled? Like it's not as apparent as it is in the Lagrangian perspective.
Very good, very good. So in the Hamiltonian formula, in the phase space formulation, relativistic symmetry is not manifest, right? However, there is something called the covariant formulation of the phase space. We're not going to talk about that in this class, but indeed, there's a way of doing this, constructing the phase space fully covariantly. That ties in with the story of symplectic manifolds, and it's a reformulation of classical physics that takes you a few steps forward. Like there's a whole, if you ever take advanced classical physics, classical mechanics from Arnold or whatever textbook, that's what they're going to teach you guys. That's going to be essential for some theories that are like gauge theories or gravity. Covariant formalism is often, it's a little bit more cumbersome to work with, but it keeps symmetries manifest. But as you observed, precisely, Lagrangian formalism keeps the Lorentz symmetry very, very manifest, right? Is it clear? So just to clarify the comment, the question. So every time we go to the Hamiltonian picture, it involves picking a slicing of space-time into time and space, right? I define time, I fix time, I pick a hypersurface, a constant time slice. That breaks Lorentz invariant. That's picking a set of coordinates, right? It doesn't break, it just makes it less manifest, right? All right, did I answer the question?
Yeah, actually, about that, I had another related question. If going to the Hamiltonian perspective, models this, it does not make this space-time invariance manifest. Why do we perform quantization using the Hamiltonian? Why not just quantize by the Lagrangian? Is there any
Depends
utility?
what you're trying to do. Depends what you're trying to do. You could do it in both ways. You could do it in both ways. There is no, if you are quantizing a complicated theory, often the way to go about doing this, and which has relativity, if you want to get yourself not confused, you use a covariant formalism. But when we use the Hamiltonians, we are not going to say anything incorrect. We're just going to be very careful about what is implied by relativity. We're going to do this. We're going to do this explicitly.
Okay, thank you.
Sure. All right. One comment for those of you guys, is very convenient that there was just a question about that. So I said we ignore the boundary terms in the action. The boundary terms in the action are the variations of the following object, right? If you just look at the expression that I've written down over there, it's sum over I pi delta qi. On the phase space, this is called a symplectic one form. This is one of the starting points of reformulating classical mechanics on the phase space as a symplectic manifold. If that doesn't tell you anything, it won't matter. We won't discuss it in this course. This is just for those of you guys who have dealt with phase space and covariant formalism. All right. So next, so in summary, what we did was that we took the motion of a classical F equal and made a motion of a single particle in space, classical physics, right? We formulated in terms of an action principle, and the principle of locality was in play. It played a very crucial role, right? Now we're going to do that for field theory, right? Along the way, we're going to find that we'll need to be careful about functional derivatives and I'll try to do a little bit of detour because that's what most textbooks just drop. And we're going to go through that, work out a few examples. I might give you a hard time in the homework because it's so easy to get yourself confused about functional derivatives. All right, so classical fields. In 0 plus 1 dimensions, you had qi of t, right? That was 0 plus 1. This is just a single particle moving in as a function of time, right? That's a field in 0 plus 1 dimensions. Now you're going to replace that with phi of t and x in d plus 1 dimensions. This I in the A index is just some Lorentz representation. For now, we're just going to drop it and say it's a scalar, right? If it's a vector field, it would be a little bit like an index like this, phi of mu or something, a mu. For example, in QED would be a mu. But it's a scalar field for now. Now, the principle of locality was in the 0 plus 1 in classical, the motion of a single particle was write down your action as an integral over time of a Lagrangian. If you want to generalize the notion of locality to space-time, you'll have to write down your action as an integral over the space-time of something that we're going to call Lagrangian density. Here, locality means integral of d of x, dd plus 1 of x, as opposed to double integrals, triple integrals, all the other things that you have. That's locality. This is the magic of field theory. This is the magic of field theory. It's a very, very powerful principle. You want to construct a theory for some field theory, you don't really know much about it. All that you care about, instead of some wacky function from like space-time to numbers, right? Functional, right? You just bring it down to a Lagrangian density that's defined at every point, right? So here's what we're gonna do. This is called Lagrangian density, and then I will use the principle of locality to write down the action functional, right? So here are a bunch of comments for you guys. If somebody knows the answer to some of this, just yell it loud. Is this Lorentz invariant? And if you want this to be Lorentz invariant, you'll have to make sure that it's a symmetry of this transformation. So what does it mean, Lorentz invariant? What does Lorentz invariant means? It means that this transformation followed by the field transforming appropriately, if it's a scalar field, if you recall how the transformation was, right? So scalar field transforms in the following way. Phi prime of x prime is phi of x side, right? You want to make sure that this thing is kept invariant. Now, if your field has a bunch of variables, there will be matrices here, representation matrices, and you have to make sure it's Lorentz invariant, right? That is the principle of Poincare invariance. Poincare invariance in general. Now, I want you guys to think about these. If you know the answer to any of these, just yell them loud. What's the dimension of the action? Does anyone know? This is dimensional analysis. What's the dimension? Tell me one parameter, one thing observable in physics that has the same dimension as action or constant.
It's joule seconds, like h bar.
It's h bar. Yeah. What is h bar? Angular momentum. Right? It's angular momentum or h bar. Very good. So if you want to get something dimensionless, you'll have to divide this by h bar. Good? That's point. We're going to need to do that later at some point in this course. What is the dimension of the Lagrangian density? Well, it's pretty clear that it's fixed from the dimension of the action and by this integral. Because the theory is local, the Lagrangian density will have a fixed dimension, right? That will tell you, that will fix for you a dimension for the fields. This is going to be crucial. Fields are also dimension-full things, right? So you want to, as a physicist, you always want to be careful about the dimensions you're using, right? So the dimension of your field is going to be important. You can get a long way with just dimensional analysis. All right, that's just a comment for you guys to keep in mind. All right, I have to speed up. Now, action is a local functional, right? What does it mean? Here's my space-time, say 2 + 1 dimensions, right? X, Y, or X1, X2 are space, and time is this direction sticking out. I take smooth functions over space-time, and a functional, action is a functional that takes as an input some function, spits out some value. Now I've written down real value, some real number, but I want you guys to think about, does it have to be real or can it be complex? So to just help you, this is where things get a little bit icky, but you have to do all it takes is just like a bunch of examples to familiarize yourself how functionals are different from functions, right? So let's just remind ourselves what functions and their derivatives are. A function on space-time takes as input a point on the space-time. So it's a map from the space-time, say it's a complex function to complex numbers, right? X mu goes to f of x mu. Now you can define a derivative of a function as a gradient, right? So you pick a direction, right? And you define, this is directional derivative because we're in space-time and there's more than one dimension, right? So this is just the standard good old definition. Now, if you have a functional as an input, you take a smooth, C infinity means smooth. Smooth function of space-time. I say smooth because I want to take derivatives. And send it to say complex numbers, right? So f goes to s of f. All right. To just understand what exactly are we doing, it's helpful to discretize space so that we can relate the two stories. So f of x as a function over space-time, if my space were discrete, is just a collection of numbers. f1, f2, f3, the index I is the I side, I's point, right? Now, a functional takes as an input a collection of these f1, f2, f3, blah, 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 spits out something. For example, it could be fi, fj, cijk, l, and sum over all these things, right? Is this step clear? So a functional is in principle an ugly thing, right? But luckily, because of locality, it's not that bad. Now, what does it mean to do an infinitesimal variation? Well, here was what your function. Just do delta f1, delta f2, delta f3 at each point. Move this. So when you move this function to a new function, I don't know this. Your variations are, there's one variation here, one variation here, one variation here, one variation here. Those are your delta x, right? All right, so your s of initial function goes to s of a new function. I have put some Kronecker delta here. So I've written delta fk as identity matrix acting on delta fk. I want to view these points on a lattice as a matrix. There's a reason for that. This trick, I absolutely recommend you guys to put extra Kronecker deltas in these examples because you're going to see it will be helpful in field theory. So if you want to know the variation of S with respect to Fi, now that I discretize, Fi just is a variable, right? It's a simple function. It's just a normal good old function derivative. And this is the definition of the derivative. Right? So by discretizing my point, I just turned a functional to as my space, turn a functional to a function of many variables, right? That I can take a derivative with respect to each one of them separately. Now, when I take this formula, right? When I take the continuum limit of it, gives me this. So now I know exactly how to take a variation, how to vary a functional with respect to a function. There's an interval over space-time that sticks out, comes out. Are there any questions? We're going to go through 3 examples. And hopefully 1 example in your homework. All right, some examples. Take as your functional a simple expression like this, right? This is let's say 0 plus 1 dimension, y is time, for instance. It doesn't matter for this purpose. It's just we're doing some exercise in functional calculus, right? So this is your function. You just follow the laws that I described to you. Del S del fx, right, is this expression and is equal to 1. This is your Kronecker delta. So now previously you had I and K, they become Y and X. Your Kronecker delta becomes a Dirac delta function. Does everyone know what the Dirac delta function is? It's nothing really fancy. It's just this thing. It's a distribution that integrates to 1. So it's something that everywhere in space is 0 except for the point 0, where it takes a value that's infinite such that it integrates to 1. Right? So it's a distribution. It's not a function. All right. Well, I'll go through these a little bit fast, but you have the examples and you can do them in your spare time to get familiar with yourself, and I absolutely recommend doing this with functional calculus, because otherwise you could get yourself really, really confused. So another type of linear functionals that appear a lot in field theory are linear functionals with a kernel, where your S of f has this extra variable, say x, and it's defined in this particular way. And this is a kernel. This is what it means to have a kernel. When you do the derivative, you basically get the functional derivative spits out the kernel. Both of the examples were straightforward. Example number 3 is perhaps the trickiest one, and I want you guys to think about this, because this is what we're going to use immediately. Now, let's say my functional is a function of the derivatives of the field. So an expression like this, right? So now what I have to do is that, following the prescription we had, I have to shift phi of x to phi of x Dirac delta function, delta of x squared, the whole thing. Following the rules that I just explained to you guys, if you take a functional derivative of action with respect to phi of y, you get integral of d of x, derivative of Dirac delta function, del x of phi of x. That's just like going step by step. That's what here if you don't put the Dirac delta function, you can get yourself confused. Actually, that is why I put this by hand. Now, how do you evaluate this integral? Well, you do integration by parts, as we often do with these expressions, right? So you complete the square and basically you write it as a total integral minus this term, right? The total integral as a boundary term vanishes. This is all you've got. The del x is now flipped and put on phi of x, right? And when you do the integral, you get the second derivative of phi of y at point y with a coefficient -2. I encourage you guys to walk through this slowly, just go through it a little bit slowly, because it is an integral that we're going to be doing over and over and over again all the time. All right, any questions? So
in the second example,
yes.
for the blue expression, should the integrating variable be y or x?
Oh, sorry, it's y. Thank you. That's a typo. Thanks so much. Yes.
And also about the delta function, I see that in these expressions, the delta function has 2 arguments. So this is the 2-dimensional delta function, right?
Yeah. So one of the arguments is this z. Right?
Okay.
No.
Okay.
Yeah. This is not a 2-dimensional thing. It's just maybe that was it's something like this.
All right. I see.
The Dirac delta.
Thank you.
It's not 2-dimensional.
Yeah. Okay.
Yeah. Maybe my notation is confusing. All right. So in summary, these are examples to just remind you guys, functionals are different from functions, and you have to be careful when you take derivatives. There are laws that you could describe, you could go through them step by step in your head. Once you discretize the functionals and view them as a whole bunch of functions, right? As a whole bunch of variables, right? All right. Finally, we are finally in a place that what we can just formally do the variational principle for a field theory. So this is a generalization of that classical mechanics example we just went through that was 0 + 1 dimensional to fields in space-time. So field, you have a functional, which is action. You want to calculate this variation. And here's what the variation is. And this was our working definition, right? This was our working definition of what the variation is. All right, so let's do that. All I have to do is that I have to take functional derivatives of S functional action with respect to the field. All right, so I get two terms. One comes from the variation of del phi. The other one comes from the variation of del mu of phi. This is similar. Previously, we had our Lagrangian was a function of q and q dot. So I got two terms, one from varying with respect to q, the other one from varying with respect to q dot. So here is playing the role of q. This is playing the role of q dot. This is playing the role of q, right? Now, here, the fact that you have space-time tells you that instead of q dot, you have all derivatives in the spatial directions in time. So now your locality is a lot more restrictive. You're not only you're local in time, but also you're local in space. That's why field theory is so powerful. It maximally uses the notion of locality. All right. So as before, what we have to do is that we have to do integration by parts, but this is a good exercise for you guys. This is integration by parts for functionals, and it basically puts this it basically puts this delta over all of it and gives you as an extra term this capital D mu. Capital D mu is a total derivative of a functional defined in the following way, and you get a boundary term. Now again, if you have Dirichlet boundary conditions or phi of x, so now your boundary term is all the way at infinity, right? Infinity in space-time, and we often, the same way that in the previous example, we're keeping Ti and Tf fixed, right? And letting this thing wobble in the middle. One of the basic principles in field theory, flat space field theory, is that we want the field to die away at infinities in space. We just let it fluctuate in the middle, right? So the fact that you want the field to vanish far at infinity, this del mu will give you an interval over the infinity of space-time, right? But del phi of x will be 0 at those points, right? And the boundary term will vanish, and this term will have to be 0. That is your Euler-Lagrange equations for any field theory, local field theory in any space-time dimension. This is a super compact notation because this capital D is this funky derivative, total derivative of the functional, right? So this is the last point I wanted to make in this lecture, but let me just summarize what we did, right? So we started by reviewing very briefly the relativistic notation. We reminded ourselves that there is this Poincare invariance, which has 3 elements to it. There are the generators that are translations, there are rotations, and then there are boosts. Rotations and boosts together form a group that's called Lorentz group, right? Then we said, if you take a single particle, classical single particle moving in space-time, right? You could formulate F equal ma, dynamical equations of that as a minimum action principle, right? We wrote down an expression, and then we emphasized the role of locality of this action, right? That was very important. We talked about the phase space way of doing it, Hamiltonian way of doing it. We talked about the Lagrangian way of doing it. And the point was that equations of motion vanishing, being true in the Lagrangian picture was equivalent to energy or Hamiltonian being independent of time, energy being conserved. We pointed this out, that this is one instance of a connection between conservation laws, conserved quantities, in this case energy, and invariance of Lagrangian under transformations, in this case time translations. Right? This is a particular example of Noether theorem. We're going to come back to Noether theorem and talk about it in full in its full capacity, but for now this is just an example. We had the Euler-Lagrange equations. Then as a next step, we took field theory, which was as a bunch of functions in space-time as our dynamical variables, right? Then our action principle is a functional, as a function from smooth, it's something that maps smooth functions of space-time to numbers. I encourage you to think about the dimensionality, dimensional analysis, but we emphasize the role of locality. Locality is manifest in the fact that you write down the functional action as an integral over space-time of something that we call Lagrangian density. Just a single integral, not a double integral, triple integral, or anything else, right? This is locality. Then we just explained some, I guess it's a sensible generalization of differentiations and calculus of functions to functionals. This was actually the main point I was trying to make over there. Every time you vary a functional, you end up with these type of expressions. Then you do this, you write down the minimum action principle for field theory, and pops out equations of motion, the so-called Euler-Lagrange equations, right? These are the Euler-Lagrange equations, dynamical equations that describe how the fields evolve in space-time, right? Okay, this is, are there any questions? All right, it was either clear or very confusing. At any rate, there's a new problem set that's posted. There's a problem set, first problem set that's posted. The videos are going to be on YouTube. If any of the links don't work at any point, I've made a mistake somewhere, just quickly send me a message on Slack. I'll fix it. And yeah, so I'll try to post some readings in advance. You already have some readings for this lecture, right? And yeah, that's basically it, all I wanted to say. Any last questions? If not, thank you so much and have a wonderful day. Bye, guys.
Thank you, Professor.